These are the section 2.1 notes on functions. So first, a function is a rule that assigns each element in one set to a unique element in the second set. A function is a set of ordered pairs in which no two ordered pairs have the same first coordinate and different second coordinates. So you might recall this is where each individual input or x value has a unique output or y value. So first, we'll look at a couple relations. Relations typically we think of as just sets of ordered pairs, or in this case a table. So we have three different inputs here, 1, 2, and 4. They each have outputs. It doesn't matter that 1 and 2 have the same output. All that matters is that the x values have their own output that is predictable. So 2 outputs a 3, 1 outputs a 3. 1 does not output more than one value. 2 does not output more than one value. It doesn't matter if they're the same value or not as each other. So since they each have specific outputs, they don't have more than one output, we're going to say yes, it's a function. This next relation is not a function, and that's because for these first 2 points, we have the same input, an input of 9, but we have two different outputs, an output of -3 and an output of +3. That makes it kind of unpredictable. If you input 9, you don't know what the output's going to be. It could be one or the other. These two pieces would support it being a function if you didn't have those first 2 points. 4, 2, and 0, 0 do not tell you anything about it not being a function. Over here, they're telling us that we have a quantity of something and the price. If you buy a quantity 1 to 5, you have $9.40 each. If you have a quantity of 5 to 10, you have $8.75 each. This would not be a function because the quantity of 5 is included in 2 places. So we're going to say no, not a function here, no, not a function here. And the reason is one input has 2 different outputs. So since 5 has 2 different outputs, that makes it somewhat unpredictable because you don't know if you're going to get a quantity of 5 and have the higher price or get a quantity of 5 and have the lower price. When you have inputs with a specific output, that's more predictable. You know exactly what you're going to get when you plug in a number. Next, if you have not just some points or a table, if you have the actual graph of a relation, then you can determine if it's a function by doing the vertical line test. So if you do the vertical line test, or some teachers might call it the pencil test, you can take your pencil and pass it over the graph, and it should only touch 1 point at a time. One x coordinate should only have one y coordinate. So this does not pass the vertical line test because the x coordinate of 2 has an output up here and an output down here. It has 2 different outputs. So this would be no, it's not a function. This one does pass the vertical line test. If you bring your pencil across, it only touches 1 point at a time. So we would say yes, this is a function. For this next one, if we did the vertical line test, you can see over here at -2, it's touching 2 points at the same time. This x-coordinate of -2 would have one y output. This x-coordinate of -2 would have a different y output. So we would say no, that's not a function. So down here, if we have a different graph and we want to determine whether y is a function of x, we would do the vertical line test, and we can see that our pencil, my pencil is really thick compared to that vertical line, but it would not touch more than 1 point at a time. So we would say, yes, this is a function. And you can think of it as like, I think of it as 2 points that are kind of on top of each other, or they're like vertically aligned. All right, next, determine whether each equation is a function. We're going to do this by thinking about what we know of how equations look. So this is y equals x squared. It's got more stuff to it, but it's an x squared, which is a quadratic equation. And those are the U-shaped graphs like this. And I know if I do the vertical line test on that, it's only going to hit 1 point at a time. So I'm going to say yes, that is a function. This next one might require a little bit more thought. In fact, it definitely will require more thought. For this one, I'm used to seeing typically, I'm going to write this off to the side. I'm used to seeing y equals absolute value of x. I'm not used to seeing x equals the absolute value of y. So if you had y equals the absolute value of x, excuse me, that graph is a perfect V. It looks like this. And when you switch the variables, what it does is it takes the graph and it just graphs it sideways. Instead of the graph opening up and down, it opens left and right. And I graphed it on Desmos and printed it so you could see it. So this is what x equals the absolute value of y looks like. So we're going to draw this graph. It looks like this. Doesn't matter where it is. The fact is, if you do the vertical line test on this, you're definitely going to have points that are on top of each other. And so we're going to say, no, this is not a function. Another way that you can tell if something is a function or not, if an equation is a function or not, is if you try to solve for y, how many equations are you going to have to write to do that? Or how many equations are you going to have to write to represent the curve on the paper? So for this first one, y is already solved for. For this second one, y is not solved for. If I had to write equations to represent this graph, I would have to write one linear equation to represent the top portion and one linear equation to represent the bottom portion. And I can see this graph, it's a straight line, it has a y-intercept of 0, and it goes up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. So for the top half of the graph, I would say this is y equals 1 over 1. Sorry, that's not what I meant to write. That would be 1 over 1 x plus 0. And this is only if x is greater than or equal to 0. And by that, I just mean that 1 over 1 x plus 0 is this whole line. And I'm not using the whole line. I'm just using this half of it, just the right half. This bottom line would be very similar, but it would have a negative slope. Down 1, right 1, down 1, right 1, down 1, right 1. So the equation of this line would be negative 1 over 1x plus 0. It still has that y-intercept of 0. And again, I'm only using the right half of the line. So you didn't have to do this. You didn't have to write these equations. But what is important to notice is that if you were to write equations for this and write them as functions, it would be one function, two functions to represent the equation. And that means it's not a function on its own. Okay, the next one is this one right here, x squared plus y squared equals 1. This is a circle. Remember, if we have x squared and y squared on the same side, that's giving you your center of your circle. The right side is giving you the radius of the circle. So this is a circle with a center of 0, 0 and a radius of 1. So if I were to kind of sketch a graph of that, center 0, 0, radius of 1, and that would definitely not pass the vertical line test. So I'm going to say no. And then I can say, well, if I wanted to, let's say, graph this on a TI-84 graphing calculator, I couldn't plug this in the way that it is, just in my y equals screen, because the y is not solved for. So if I wanted to solve for y, I would have to do I would have to take the x squared and subtract it over to the other side. And then I would have to square root the y, and anytime I square root, I get a plus and a minus. And that plus and that minus means that I actually get two equations that I would have to graph on a TI-84 graphing calculator to get the whole circle. The positive version would give me the top half of the circle. The negative version would give me the bottom half of the circle. So your TI-84 graphing calculators, those only graph functions when you're in the y equals screen. And so that can be kind of a clue about if the equation you're working with is a function or not. Is the y alone? Can I graph it on a TI-84? And if not, it might not be a function. So this one is no, not a function, because it doesn't pass the vertical line test. And if you did have to solve for y, you would have two equations. This one over here, it's got the x and the y on the same side. The y is not solved for. However, this is just the standard form of a line. It's a straight line. I don't know if it goes up or down, but it looks something like that. And this definitely passes the vertical line test. And if we solved for y, we would just get something like y equals mx plus b, some sort of fraction probably for the slope, and then some sort of y-intercept. So we can definitely solve this one for y, even though it's not currently solved for y. So that is definitely a function. Okay, let's look at the next page. So here we're going to look at the domain and the range of relations and functions. So the domain is all of the x values or inputs that are defined in the function. This means that you can plug a value into the function and actually get an answer. The range is all of the y values or the outputs that are defined in the function. These are all of the answers you've gotten after you've plugged the x values in. So what I did here is I put a list of the typical functions I could think of so that we could write down, they're called parent functions if they don't have any numbers in them, so that we could write down what all of them are and what their basic domain and range are, and then we just know that if there's some numbers involved in the equation, then things might change a little bit. So the first parent function is just linear. It's a straight line, y equals x. And if we think of the x values that are allowed in this, we can see it in the graph. This graph goes left forever, it goes right forever. That's the x values. There's no x values that are excluded here. So the domain is from negative infinity to positive infinity. The range represents all the y values that are included. Y values would be how many values go down in the graph, the values that go up in the graph, and see if there's any values that are skipped there. And I'm not seeing any y values that are skipped. With the arrows going up and down, everything is included. So the domain is negative infinity to infinity. The range is negative infinity to infinity. This next one is an absolute value function. For the domain, we can see the same thing. It goes left, it goes right. So this means that I can plug any x value into the equation that I want. Doesn't matter what the x is. I'm always going to get an answer. However, with the range, I can see that there are all these positive values for y, but there's no negative values for y. That doesn't mean that I can never get negative values for y if the equation was like y equals the absolute value of x minus 7 or something. But it does mean that the range is going to be limited for these graphs. So for the parent function, we're going to say that the very smallest y value you can have is 0, and then you can have all the y values that are bigger than 0. 0 is the smallest. All the numbers that are more positive than that will be included in the range. Next is a quadratic function, y equals x squared. You can see here, left and right, that means that any x value that I want to plug into the equation, I can. All of them will give me answers. But since I'm taking a number and I'm squaring it, just like the absolute value function, whatever I plug in is going to become positive. So the very lowest value that I can have here is 0, and then positive values from there. All right, the next one is a square root function, y equals square root x. Square root functions are probably going to be the most interesting ones that we look at for right now. We're going to look at more interesting ones later. But here, this is interesting because you can't square root every single number you can think of. We know that all the negative numbers, if you square root them, you get imaginary answers, or I. And so for the domain, if we're talking about real number answers, what can you actually see on paper? We know that you can square root 0 and you can square root positive numbers. So my domain is that I can plug in 0, I can plug in positive numbers and actually get an answer that I can see. The range is similar because when I plug in 0 or when I plug in those positive numbers, I'm going to get outputs that are the same. Square root of 0 is 0. Square root of a positive number is still just a positive number. So the range, the lowest y value that I'm going to get as an output is 0, and then that goes up to infinity. All right, y equals x to the third, and then this one is the cube root of x. You can see those graphs look very similar. So here you can plug in any x value you want from left to right. You can see all the x values are used. Same thing here. You can plug in any x value you want. You can cube root negatives. You can cube root positives. So for the domain, any x value can be used. All right, and then for the range, once you plug in those x values, the y values that the equation is going to give as a result, you're going to have all sorts of values there as well. All the negatives, all the positives. So that's true for both of those. Next, we have a rational function, and I'm addressing it now, but we are going to do rational functions in a whole chapter. So rational functions, if you look, you can see from left to right, there are negative x values, there's positive x values, but right in the middle, you skip 0, and that's because you can't divide by 0. 1 over 0 just doesn't work. So for the domain, we're going to say, use all the values, but skip 0. And the way that you write that is you say negative infinity to 0, and you put parentheses around it because you're not including 0, u 0 to infinity. So all the numbers but skip 0. The same is true for the y values. So we'd have all the negative y values, all the positive y values, but not 0. Not the middle. And the reason for that is that if you have a fraction, 1 over some number, that fraction could never equal 0. The only way you can get a fraction to equal 0 is by having 0 on the top, and the top is always 1. So for the range, we're going to say negative infinity, 0, 0, infinity. So this one is a pretty interesting one to find the domain and range for, but we'll be doing that in a different unit. This next graph is an exponential function, y equals 2 to the x, y equals 3 to the x, y equals e to the x, y equals 5 to the x. These graphs, when you're plugging an x value in for an exponent, you can plug in any value that you want for x. Negative values, positive values, all of them will work. However, for your outputs, once you plug those values in, you're never going to get 0. Even if you plug in 0, 2 to the 0 is 1, so you're not going to get 0 with that. Negative exponents, 2 to the negative 2, doesn't give you a negative number, it just gives you a fraction. It just gives you 1 over 2 to the second power, it just gives you 1/4. So there's no way to make this expression equal 0, there's no way to make it equal a negative. So the range would be from 0 to infinity, but you can't include 0. It's never going to equal 0. This is another one that we're going to study on its own. The last is y equals ln x, which is log base e of x, or log base 2 of x would look similar, log base 5 of x would look similar, log base 10 of x would look similar. So for these, there's some limitations on what you're allowed to plug in. You can't take the log of 0, and you can't take the log of a negative number. So here you can see that this graph is on the right side of the y-axis, and that's because the domain is from 0 to infinity. Not including 0, you can't plug in 0. And then the range, you can have any output you want. You can have negatives, you can have positives, all of the numbers for the outputs will work. And that is one we'll also be studying more later. Okay, so having this will be really important in your notes to have, because if you're expected to state the domain and the range for a relation, or even to just determine if it's a function or not, it's good to know which equations correlate to which pictures, and to be able to use that to think about what the domain and range could be. So first, we have domain and range of just some points, and so that's pretty easy. The domain is just the x's, and the range is the y's. And so when we have specific numbers that we're going to put, we do the little set notation, the squiggly bracket. So -1, 3, 3. So just -1 and 3. Since the 3 is used twice, I don't have to write it twice. For the range, I have 1, 9, and -9, and I'm going to put them in ascending order, so getting from smallest to biggest. So -9, then 1, then 9. So that's the range. This one, I don't have to know exactly what this looks like. 2x plus 3y equals 12. That's a standard form for a line. So I don't care if it goes up or down. I just know that it's a line. And I know about lines that they go left and right forever. You can plug in any x value you want. It's always going to work. And that your outputs, you're going to have all sorts of outputs, negatives, positives. No numbers are going to be skipped. So my domain is -infinity to infinity. My range is -infinity to infinity. Okay, this next one is a circle. It wasn't on the list because it's not a typical parent function. It's not a function, that's why. But we can think about what the graph of a circle would be, and then think about what x's and y's are involved. So this circle has a center at 3, -4, and it has a radius, the square root of 4 is 2. So the circle has a center of 3, -4, and it has a radius of 2. So if I were to just sketch a graph of this, the center is 3, -4, and then from there we go up 2 and down 2, right 2 and left 2. So up 2, this point would be 3, -2. Down 2 would be 3, -6. To the right 2 would be 5, -4. To the left 2 would be 1, -4. So this is what my sketch of the circle would have looked like. And this kind of tells me my domain and range. How far to the left and right does the graph go? How far up and down does the graph go? The x values of all the points on the circle are going to fall between 1 and 5. All of the x coordinates are going to have to be between there. So my domain is from 1 to 5. My range values, my y values, are going to fall from -6 to 2. All the y values are in between those two numbers, -6 at the very lowest, -2 at the very highest. Okay, the next one is a square root graph. And this one is the one you really pay attention to because this is the one that is kind of specific to this unit. This is the funky one that we're looking at for this unit. So square root graphs have the special property that you can't square root a negative. You can square root 0, but you can't square root a negative. So if it's just square root x, then you just know, okay, it's going to go from 0. You have 0, 0 is kind of the starting point, and it goes from there. Well, this example has some numbers in it, so it's not going to be at 0, 0, it's going to be somewhere else. So I just have to think about how this right here must be greater than or equal to 0. Has to be, because that's how square roots work. So I'm going to write 2x minus 1 is greater than or equal to 0, and then I'm just going to solve for x. So I'll add the 1 over to the other side, and then I'll divide by 2. So it says x is greater than or equal to 1/2. So what that means is for this particular graph, the x coordinate for this starting point right here is a 1/2. That's the x coordinate of the starting point. So if I were to draw a little sketch of what this graph would look like, I know that it would look something like this, and that the x coordinate is 1/2. So I can already tell that the domain starts at 1/2, I can plug in 1/2, and then it's going to be all the numbers bigger than that. Those are going to be the numbers that work in the equation. Now the outputs are going to be whatever that corresponding y value is, some sort of y value that goes with this point right here, and then everything up from that. So the range is some corresponding y value, and then it goes up to infinity. And for me to find that corresponding y value, I just have to plug 1/2 in. So 2 times 1/2 is 1. 1 minus 1 is 0. And the square root of 0 is just 0. So this point is 1/2 0. And the range must be from 0 to infinity. And I got a picture of this as well. So this is what that graph looks like. It starts at 1/2 0, and then it goes up forever, and it goes to the right forever. So the domain is from 1/2 to infinity. The range is from 0 to infinity. All right, next, let's look at some function notation. So function notation just allows you to write your equations. Instead of writing as y equals, you say f of x equals, g of x equals. It's a way to give your equations different names. So f as a function of x, it just means some equation written in terms of x. G as a function of x, some equation written in terms of x. K as a function of x, it's just some equation written in terms of x. So we'll start with the first one. It says d, which is a relation up here, d. If I plug in 7 for x, what's the corresponding y coordinate? So I look, there's 7 for x, the corresponding y coordinate is 9. The next one says plug in 7 for x and find the corresponding y coordinate. So 7 for x, this would be the square root of 4, which is 2. So if I plug in 7 for x, then I get 2 for y. The next one says find x if g of x equals 14. So if I take g of x and the answer is 14, what would x have to have been? Well, I'll just go ahead and solve this equation. So I'm going to add 2 to the other side. X squared equals 16. And then to solve the equation, I need to square root. And so the square root of 16 is plus or minus 4. So there's 2 answers here. Positive 4, negative 4. Next it says to find g of a. G of a is kind of nice. All you have to do is just stick the a in there. So g of a is going to be a squared minus 2. And that's it. You're done. A squared minus 2. The next one, g of a plus 1, that one takes a little bit more thinking. So g of a plus 1, we're going to say g of x is something squared, x squared minus 2. But instead of taking an x and squaring it, we're going to take an a plus 1 and we're going to square it. So a plus 1 times a plus 1 with a minus 2 on the end. And we have a squared plus a plus 1, and then the minus 2 on the end. So this is a squared plus 2a, 1 minus 2, minus 1. This one is like a combination of those previous 2 problems. It says take g of a plus 1 and then subtract off g of a. So g of a plus 1, we would do plug something in for x minus 2. So this is g of a plus 1. I'm plugging in a plus 1 squared minus 2. So g of a plus 1 minus, and then g of a, I'm going to have to minus that whole group, is a squared minus 2. So this is g of a plus 1 minus g of a. I already know what this is. I've done the work, so I'm just going to substitute it in there. It is a squared plus 2a minus 1. And then subtract off g of a. So I'm going to distribute my minus a squared plus 2. So I have 2a plus 1. Okay, let's try that process, or a similar process again. So we have k of x is 2x minus 3, and they're telling us to plug in x minus 2 for the x. So I'm going to write 2 times something plugged in for x minus 3, and the thing that I'm plugging in for the x is x minus 2. Alright, so I'll go ahead and distribute to get rid of the parentheses. 2x minus 4 minus 3 is 2x minus 7. Here they're saying take the function and plug in x plus h for x, and then just subtract off the whole function. So k is 2x minus 3. So I'm going to do 2, plug something in for x minus 3. The thing that I'm plugging in is x plus h. And then from there it says just subtract off the whole function. So subtract the whole function, which is 2x minus 3. Alright, so I'll go ahead and simplify. 2x plus 2h minus 3 minus 2x plus 3. Okay, so 2x minus 3 plus 3. That leaves us with only 2h. Okay. Next we want to talk about average rate of change, which is not a new idea to us. It says if we have x sub 1, y sub 1 is the first point, x sub 2, y sub 2 is the second point, so that's two ordered pairs or 2 points from a function. We define the average rate of change of the function as x varies from the first point to the second point as the change in the y coordinates divided by the change in the x coordinates, change in y over change in x. This should be familiar to you. The average rate of change is also known as the slope. So in the past we've looked at slope of a straight line. Now we're looking at the approximate slope of a curved line by just finding the average rate of change of 2 points on that line. So if we want the average rate of change on 1, 3, these are x values. They're saying starting at x equals 1 to x equals 3, what's the average rate of change? So what we want to do is we want to find the corresponding y values. So we're going to say f of 1 is plug in 1 for x, 1 squared, and f of 3, we'll plug 3 in for x, we get 9. So the formula would be to take the first point, plug in 1, and then f of 1 if I'm writing function notation, and then 3 and f of 3. So we would say y minus y divided by x minus x, or based on the numbers we found, 9 minus 1 over 3 minus 1, and this would be 8 over 2, which is 4. So the average rate of change between these 2 points is 4, or the approximate slope of that curve would be 4. Now, the way that we use this in pre-calculus is this way with the difference quotient, and I'm going to show you how we find that. So we're going to do the same thing. We're going to say we have one point, x, f of x, and we have a second point. That point is over here, and it's some distance, some unknown distance away from x. I'm going to say that this is a distance of h. And so this x value over here, if this is x, and this is a distance of h, then this x value would be x plus h. So this point is x for the x coordinate, f of x for the y coordinate. This other point would be x plus h for the x coordinate, and it would be f of x plus h for the y coordinate. So this is our first point. Here's our second point. And if we wanted to find the average rate of change between the two, we would just say the y minus the y divided by the x minus the x. And you can see that on the top in the numerator we have f of x plus h minus f of x, and on the bottom positive x and negative x cancel and we're just left with h. And this is just called the difference quotient. So it's kind of like a formula to find the average rate of change on a curve instead of a straight line. So here we know that the difference between this y coordinate f of x plus h and this y coordinate f of x, the difference between those would be f of x plus h minus f of x. So if you did rise over run, this would be your rise, this would be your run, or this would be your change in y's divided by your change in x. It would be your approximate slope or your average rate of change on the curve. So for these examples, they're asking us to find the difference quotient, which is just asking, hey, can you give me a formula where I could find the slope between 2 points if I wanted it? So that's what we're going to do. We're going to find, for the first one, f of x plus h minus f of x over h. So f of x plus h would be 3 times x plus h plus 2. So there's the f of x plus h minus the function itself. So minus the function itself. And then divide this by h. And we're going to simplify. So 3x plus 3h plus 2 minus 3x minus 2 divided by h. So your 3x's cancel, your 2's cancel, and you're left with 3h over h. And h divided by h is just 1. And 3 times 1 is just 3. Which makes sense, right? Because the slope of a straight line, it's not a curve, the slope is always going to be 3. So this, no matter what point, if you pick any pair of points on that line, their slope is going to be 3. Okay, let's try the next one. So this one, it's g instead of f, so we're going to say g of x plus h minus g of x divided by h. So g of x plus h would be x plus h squared minus 2x plus h. So I took the function and I plugged x plus h in for x. X plus h goes in for x. Then I'm just going to minus off the whole function. So minus x squared minus 2x. And this whole thing is going to be divided by h. So I have to be careful because this one right here, x plus h squared, I really need to write that twice so I can FOIL it out. But these other parts I can just distribute. So I have a negative 2 that I'm going to distribute here. Negative 2x, negative 2h, negative x squared, plus 2x. Okay? And now I can go ahead and multiply this out. I have x squared plus xh plus, that's another xh, plus h squared. So x squared, 2x. So I'm left with, I have one xh and another one xh, so altogether that's 2 of them, plus h squared minus 2h, and all of those are divided by h. So I can divide by h on each of these as long as I do it to each term, it's allowed. So divide by h, divide by one of the h's, divide by h, divide by h, and so what I'm left with is 2x plus 1h minus 2. All right, let's look at the next one. So this one says j of x plus h minus j of x divided by h. All right, so I'm going to take the function, I'll plug in x plus h minus the function itself over h. And the book does more simplifying than that. All of this is a true pre-calculus concept. You're learning this because in calculus this is important. And I think that the way that the book does this doesn't make sense to learn in pre-calculus. So I'm going to have you guys leave it here. We're going to stop right here and call this the answer. All right, let's do the next one. So we're going to have k of x plus h minus k of x divided by h. Okay, so I'm going to take the function, plug in x plus h, minus off the function itself, divided by h. There's a couple ways that you can simplify this. The common practice that I've seen, it may not be familiar to you now, but the common practice that I've seen moving forward is to find the common denominator between both of these pieces and multiply. So for the denominator, you need x plus h and you need x. So I'm going to multiply by x times x plus h to the numerator and x times x plus h to the denominator. And I'm allowed to do that because it's like multiplying by 1. If I do the same thing on the top and the same thing on the bottom, it's like I multiplied by 1. My problem's going to look different, but it's going to equal the same thing. So I can take this and multiply it by this, and take it and multiply it by this as well. So 5 over x plus h multiplied by x times x plus h, minus 5 over x multiplied by x times x plus h. And then on the bottom, we have an h and an x plus h. Now, this part you don't usually have to write down. I wrote it down because this might be your first time seeing it, but you can do this part in your head. So when you multiply, I can see that the x plus h multiplied and the x plus h divided are going to cancel each other out, and I'm going to be left with 5x. When I do this part, I can see that I have the 5 right here. The divide by x and the times by x, those are going to cancel each other out. And I'm just going to have 5 times x plus h. I switched these because it feels weird to write hx. Okay. So what I have now is I have 5x minus 5x minus 5h divided by xh, x plus h. These two cancel, 5x minus 5x, they cancel. And so I have negative 5h over this denominator. And then I can't touch the x plus h inside the parentheses. It's kind of protected by those parentheses. But negative 5 times h and x times h, the h's are being divided. So times by h, there's a divide by right here and then an h down there. These h's can disappear. So I have negative 5 on the top, x times x plus h on the bottom.